Hello everyone. Today we will be going over how to make a cosine generator, since that was the topic you guys voted for to come next. But yeah, now that this channel is starting to be taken seriously, I'm going to continue working harder to make each lesson more polished, and more effort's going to be spent editing the content, and even old lessons that were mediocre will be redone. Um, to help that process, feel free to comment on what things could be better or what you don't understand each video, since the end goal of this playlist is to obviously get a full-blown course made that allows any motivated person to be converted into an expert within a few months of binging. If I don't get feedback from real learners, I can't make that mission a reality. Also, if you want me to keep pumping out even higher quality stuff, consider purchasing the online course content when it gets released. The link for that is going to come out in a couple days, so just hang tight on that. But yeah, if you guys want this channel to grow, consider investing in that effort when the time comes. Alright, so this is the cosine calculator module that we're going to be designing today, where it takes in a fixed point number for the input x, because cosine is always cosine of x. Feed in that x number, then you get an output. So we feed in our input x, then we're going to get our result. It's also going to be a fixed point number with 4 bits of integer, 32 bits of fraction. And we only need 4 bits of integer because cosine, if you can remember, it only oscillates between small range, so between 1 and -1. So we only need just a couple bits of integer. No big numbers are going to be there. So that's what that does. And just to show you the end behavior, let's show you the simulation. So the simulation here, when x is 52.47929, we get -0.599. You can confirm that with a calculator. Then again, when x is -104.95, we get -0.28. And as usual, we have a start pulse to initiate the calculation. So here, after we set x to our value, we then apply a start pulse. Then sometimes after, it gets this value and initiates a done pulse. Then here, we change it to 104, then we make a start pulse. Then sometimes after, it finishes calculating and makes a done pulse. So that shows that it's working. So now let's go over the process involved in designing the source file for the cosine calculator. So to make the cosine calculator, we need to think about how the cosine function works. It's this huge oscillating thing, and let's say we want point x3 and x1. Well, what we can do is we can store this entire period. So whenever the x value is x1, the circuit will just look up in memory what the answer is and tell you. Same thing if it's here at x3. It's going to take that x value, and then it's going to know this x value corresponds to this y value. Let's output that y value. So, but you might be wondering, well, can we just store all of these values? Well, in theory, you technically could just store all x values and then have all y values in a table, but that's extremely inefficient. That will require way too much memory. So in practice, what we do is we only store a single period from here to here, because remember, the whole thing repeats. This side is the same as this. This here is the same as this. So for any x we want to evaluate, we just have to find its equivalent x value within the first period. Like, for example, for here x2, Before we can take the cosine of it, we have to shift it over 2 periods, 1, 2, to get x1. Then, using x1, we can use the lookup table to get the result. And that will be, because if you look here, this point and this point, even though we have two x values, one is negative 11.86, one is 0.7, they both return the same y value of 0.76484. So, and again, for example, if we have x4, before we can take the cosine of it, we need to shift it over 3 periods. 1, 2, 3. Then using x3, we can take the value from the lookup table and use that as our output. So, how do we know how many periods to shift it over? Well, all we have to do is divide the current x value and round down to get the integer part of how many periods, or just the integer of how many periods. So, like for x4, that original x value is 23.2832. If we divide that by 2 pi, we get 3.706. If we round down, we get 2. We get 3. We get 3. Sorry about that. And there's also a tiny little mistake here. So, and again, for example, if we have negative 11.8837 as our first value, like we want to get the cosine of this, well, we need to know how many periods to shift it over. Visually, we can see it's 1, 2, but the hardware needs to do math, so we're going to take that value, divide by 2 pi, we get negative 1.889, then we go down. We round down, we floor it to get negative 2. So we know that we went 2 over. 1, 2. Well, so once we know how many times to shift it over, how do we know the exact x value to use? Well, if we do the original x value minus the number of periods shifted times 2 pi, we get the final value to use. So for example, when we do this step on the evaluation of x4, we get the work below. So we have our x4. Then we, after doing these steps here, we can tell that the number of periods it's going to be shifted is 3. Multiply that by 2 pi, we get 6 pi. So that's 3 times 2 pi, that's 6 pi for that first part. Then, so we know that this portion here for that example is 6 pi. Then we have our original x value. Well, the original x value is x4. So the original x is this distance here. So this distance, it's lagging. This distance minus this distance is the same as this minus this, because this original x value is this. Number of periods shifted times 2 pi is this. We subtract those and we get the final value, which is this. And that final value between here and here is the same distance in the first period from here to here. Then we know we have our x3 because the final value is equal to x3. Then we can look up in our table what x3 is. So once we have our final result, once we have this distance here, which in our previous example was x3, once we are able to derive the x coordinate x3 from x4 through doing the steps previously outlined, like once we have that value, how do we get the final result? Well, what we need to do is we need to feed that value into a lookup table, because once we get final value, the x3 coordinate, that final value is going to be it's going to be a signed fixed point number, but it's going to always have a 0 in front because this is a positive distance. It will always be positive. So we can treat it as unsigned. So what we need to do is take that unsigned number, use it as the input of a memory unit, and then that memory unit will output the result of it'll output the y value. So for example, let's say we have our memory unit, and our memory unit is expecting a 19-bit address. Well, if our memory unit expects a 19-bit address, then we need to make sure that our final value here is expressed in 19 bits. So we need to have it be such that it's 19 bits and expresses the value of x3. So a good radix could be 3.16, since that radix will express all the values with enough integer bits to cover the range from 0 to 2 pi, but also enough, because remember, unsigned with 3 bits, that means it can go up to 7. 2 pi is 6.28, so having 3 bits is enough. And then having 16 bits of fraction means that it will be as precise as possible. So this is actually the smartest possible radix to choose under those hypothetical constraints. So for example, with this radix, the memory unit expects this radix when the address is all zeros. Well, all zeros with this radix means 0. So the output of that memory unit would return a different signed fixed point value that corresponds to the cosine of 0. And you get to choose what the output radix is. And again, for example, let's say we have address 1. Well, a bunch of 15 zeros with a 1 at the end in this radix is equal to this number. So the memory unit would need to return the output of that in the radix of our choice, obviously. And another example, if we have 0, 0, 1, 1, then zeros all after, well, that address in this radix is 1.5. So we would need to make it have it be such that at that address, the equivalent the equivalent signed fixed point representation of 1.15 would be shifted out. So that's how that works. So you might be asking, well, how do we initialize that memory unit with all these values? Well, the way I typically do it is just a simple AI prompt for this problem. We'll give you a Python program that lets you generate the entire memory file in under 5 minutes. It's not at all that complicated to do. It's simple enough that AI can just do it if you explain it. And making a test bench to continuously read out this stream is the second step to take afterwards to definitively prove that your memory is storing 1 period of cosine. So yeah, this whole process, very important. I will likely make another video clarifying it in case you are confused. But leave a comment if you would want that video, or if you fully understand this. So that gives me feedback on whether or not it's worth making another video, or if this is already clear enough. So now that that has been discussed, now we can put together, now that we've discussed all of the theory of the logical step that can be taken in hardware, we can finally summarize the hardware level algorithm. So we need a divider, a floor, a multiplier, a subtractor, and just a random access memory unit that takes in the start pulse. So the divider divides the x by 2 pi. The floor rounds down, multiplier multiplies, subtractor subtracts, then a memory unit to fetch the value. So we have 2 examples here showing each stage of the process from their respective hardware. So yeah. So now let's go over into how the code works. So here is our Verilog module implementing our hardware level algorithm that we discussed earlier, right here. So you can recall, these are our ports. So we have all of those defined here. We are using these radixes, 16.32 for our input, 4.32 for our output. And they're both signed. And if you remember, all the hardware level algorithm requires is a divider, floor, multiplier, subtractor. So first step is we divide. We are dividing x and by 2 pi according to the algorithm. And since x is in this radix, we need to have a parameter made for 2 pi in that radix. So that's what this wire is. And we configure our divider to handle inputs of this radix. Then we make our output width pretty wide so we don't lose any precision. Then immediately after that, the next step is to floor it. So here we take the quotient of the previous one, and the radix of the quotient as defined by this was 48.32. So we need to make the floor process an input of that radix and have an output of that radix. And all the floor does, if you can remember, it just rounds down to the nearest integer. So then we get quotient floored in that radix. Then all we do is we use a multiplier to multiply that by 2 pi. And because this was the radix input, we needed to make another parameter using the same radix and configure the input ports to be compatible with those radixes. And also making the product be pretty wide so that no precision is lost. So this wire here is defined there. And yeah. And then the final step is, final two steps, is to do the subtraction. So if you can remember, step 4, subtractor, 1, 2, 3, 4. Now we subtract. Then after that, we use our lookup table. So in most of these lower level modules, the fixed point divider, the multiplier, the subtractor, those three were discussed in the fixed point section. So feel free to review those videos if you want to understand those lower level modules. And the ROM, very just a simple memory unit, very basic. And the floor, well, yeah, that I'll just go over. Well, yeah, that very simple too. All it does is just round down. So yeah, so that is how you implement the cosine function in hardware. And again, in a couple days, the course is going to be released, the online book with the secret playlist and the Discord channel, where you can contact me for consultation directly. All of that's going to be released in a couple days. So if you're passionate about this and you want to get access to the files, consider getting that. And if you're not that passionate, that's all right. But please leave a comment on how you think the video could be improved, or on how you feel, and like and share it. And yeah, because all of those things help. All right, thank you, and see you next time.